In this DeBacco University video, we're going to go over the variation of physical properties across a period or a row in the periodic table so you can get an idea of some of the trends that occur and the predictive power that you have once you understand these trends. All right, let's start here with the atomic radius. Now the trend is it decreases across a period. So if we take any example row or a period here, we go from essentially from left to right, you can see overall there is a general decrease in the atomic radius. Yes, there might be a couple abnormalities, but in general, you're seeing a decrease in that. You could also see when you graphically represent it here, which are the ones that have the largest. Well, lithium, and we go right down here. So again, lithium to beryllium, going all the way to neon over here. And we see we go to sodium, we jump up again, and we decrease, jump up to potassium, decrease, so on and so forth. Now keep in mind, in this area is highlighted, those are some of the transition elements, and those are the ones that can have increased variability. Going on to ionic radius, for cations, they decrease across a period. For anions, they increase across a period. Remember, with cations, those positive charges, they're losing electrons, so therefore that ionic radius will be smaller. And the opposite is true for anions. They're gaining electrons and their radius is therefore becoming larger. Melting and boiling points, you can kind of see the temperature graph here. They vary in a nonlinear pattern, peaking in the middle of a period, often around group 14, and decreasing towards the right. So we kind of see that hot map, that highlight kind of in that more center region. The metals, which again is the left side, the side of the periodic table, have metallic bonding, with melting points increasing due to more delocalized electrons contributing to a stronger bonds as nuclear charge increases. For example, magnesium has a higher melting point than sodium, and we can see those two located right here on the periodic table. Covalent network solids in the middle, that's a silicon carbon as a diamond, form strong covalent networks, leading to very high melting points. This is, for example, silicon's covalent lattice. Non-metals on the right side of the periodic table, such as phosphorus, sulfur, chloride, form simple covalent molecules with weak intermolecular forces, resulting in lower melting and boiling points, and the van der Waals forces of chloride would be one example of that. Progressing on to density, generally this is going to increase across a period, peaking around the transition metals, which is the D block of the periodic table, when periods include them, but drops for nonmetals. We kind of see that trend here as we're looking at plotting density compared to atomic number. See a trend in one way, and kind of this kind of building up in that increased density, and then it kind of decreases, and it builds up, and it kind of decreases yet again. Electrical conductivity, overall, it's decreasing across a period from left to right. On the left, metals such as sodium have delocalized electrons, enabling high conductivity. As nuclear charge increases, elements transition to metalloids in this region, such as semiconductors like silicon, and nonmetals which lack free electrons due to covalent bonding or molecular structures, which is why you see that overall decreasing of electrical conductivity. Lastly, we've got the metallic character, and this decreases across a period essentially. So we can see here if we're going down a family or a column, metallic character would increase, but as we're decreasing from left to right, we're seeing the decreasing of this metallic character. Remember, your metals are on the left side, your non-metals are on the right side. Just to keep you on your toes, metallic characters increases from right to left, so kind of the opposite there. So whatever way helps you to remember it, these are hopefully providing you with some helpful trends of the periodic table.